Continuing on physical chemistry, now we're starting chapter 6 with section 1. We're going to talk about reaction equilibrium in ideal gas mixtures. First, let's talk about a pure ideal gas and the condition for reaction equilibrium. So the sum over all the substances I, I'll go ahead and write that in, but it's kind of redundant. The sum over all the substances I of nu I, remember nu I is the stoichiometric coefficient, of mu I, remember mu is the chemical potential of substance I, is going to be equal to 0. That's our condition for reaction equilibrium. So remember, nu I is going to be greater than 0 for all the products, and nu I is going to be less than 0 for each of the reactants. Now remember, we said that chemical potential is a function of temperature and pressure. Mu is an intensive property, and it is a state function. Now the Gibbs equation for Gibbs energy, the differential of the Gibbs energy is equal to minus the entropy times the differential of temperature plus volume times the differential of pressure, at least for a pure ideal gas. Now we're going to divide by n to get an intensive form of that equation. So we're going to have the differential of Gibbs free energy divided by n is going to be equal to minus the entropy times the differential of temperature divided by n plus volume times the differential of pressure divided by n. Now remember, we said for a pure substance at least that mu is equal to the molar Gibbs energy, and the differential of mu is equal to the differential of the molar Gibbs energy. So substituting in what we have there, we have the differential of the molar Gibbs energy is equal to minus the molar entropy times the differential of temperature plus the molar volume times the differential of pressure. So that gives us that the differential of mu is going to be equal to minus the molar entropy times the differential of temperature plus the molar volume times the differential of pressure. Remember, mu is chemical potential. So let's assume that we have constant temperature. So that means that the differential of temperature is going to be equal to 0. Then the differential of mu is going to be just the molar volume times the differential of pressure. Now using an ideal gas then, we can say that molar volume is equal to RT over P. So we have the differential of the chemical potential is just equal to R times the temperature divided by P times the differential of P. Now let's integrate both sides. So we're going to have the integral from state 1 to state 2 of the differential of the chemical potential is going to be equal to the definite integral from state 1 to state 2 of the gas constant R times the absolute temperature divided by pressure with respect to pressure. So we're going to have, integrating the left side, we have just the chemical potential at whatever temperature, we're assuming constant temperature, remember, and pressure 2, that's the final pressure, minus the chemical potential at the same temperature, but the initial pressure, and that's going to be equal to RT times the natural log of pressure in the final state divided by the pressure in the initial state. So if P1 is standard state, then P1, we can call that P prime, or 1 bar, or P naught. And then we can just say P2 is P. So mu, as a function of temperature and pressure 1, is going to be mu naught, because we said P1 was the standard state. So we're going to call that mu naught. So finding the mu that we actually want, the mu at whatever final temperature, is going to be mu naught at the same temperature plus RT times the natural log of the pressure divided by the reference pressure. Okay, now what about enthalpy? Enthalpy is a function of temperature for a perfect gas. Then we have the chemical potential mu is equal to the molar Gibbs energy, and that's going to be equal to the molar enthalpy minus temperature times the molar entropy. Now remember, molar entropy is a function of pressure. So the molar enthalpy is dependent on temperature, but not pressure for an ideal gas. So here's a graph of the difference between the two. Mu at temperature minus mu naught at temperature. So right where P over P naught is 1, that's our standard state, so the difference between them is 0. As the pressure increases, it goes up slowly, and as the pressure goes down to 0, it goes way down. So as pressure approaches 0, chemical potential approaches negative infinity. Also, as pressure approaches 0, the molar entropy approaches infinity? Well, we darned. Okay. So now let's talk about an ideal gas mixture. So we have the total pressure times the volume is equal to the total number of moles times R times the temperature. Now for each individual substance, the pressure of substance I, called the partial pressure of substance I, is equal to the mole fraction of substance I times the total pressure. So remember, X is mole fraction. So the chemical potential of substance I is the chemical potential of the gas I in the mixture. Now the chemical potential I star, we're saying that's the chemical potential of gas I in equilibrium with the mixture. Okay, that should be pure substance, I thought. Star usually means pure. Yeah, that's worded funny. Star means the pure substance. I'm not sure why that's worded funny there. I'll figure out why that's worded like that later. So let's say that we have this container here. We've got a permeable membrane. Only substance I can get through. So we're going to start with pure gas I. So it's at temperature, and it's got pressure of I star. That means the pressure of the pure gas. Oh, okay, so maybe star. Okay, it's been a while since I did it. So we have an ideal gas mixture here. So we have the partial pressure of I is going to be the mole fraction times the total pressure over on this side of the membrane. So at equilibrium, remember, however much I have going left through the membrane, it's going to be the same amount of I going right through the membrane. And then the pressure of I is going to be the pressure of I star. So this pressure over here is going to be the same as this pressure over here. So for phase equilibrium, the mu I mixture is going to be mu I pure. So the chemical potential of I is going to be the chemical of I of the pure substance. Now remember, chemical potential of I is dependent on pressure, temperature, the mole fraction of I, the mole fraction of the mole fraction of 1, 2, 3, 4, etc., all the way up to I. And then likewise, the chemical potential of the star is going to be dependent on temperature and then the mole fraction times the P total. That's going to be equal to the pure mu I star, which is dependent on temperature and the pressure, partial pressure of substance I. Now, Pi star is going to be the mole fraction of I times the P total, since there are no intermolecular attractions. Remember, we said we're going to talk an ideal gas mixture. So the chemical potential I star unmixed is going to be temperature, dependent on temperature, and the partial pressure of substance I. And that's going to be the chemical potential of substance I in the standard state as at that temperature, plus R times temperature times the natural log of the partial pressure of I divided by the standard state. And remember, standard state, P naught is 1 bar. 3-line equal sign means always equal to, or defined as. So we have the chemical potential I is equal to the chemical potential I in the standard state. I think that's supposed to be a T there, dependent on temperature, plus RT, natural log of Pi over P naught, when you have a mixture. Okay, that's it for section 1.